Today's topic is power factor correction. Power factor correction, where we want to talk more about AC power calculations. We want to define power factor and talk about unity, leading, and lagging power factors. And then we want to talk about power factor correction in terms of what it is and why it's important. And then we're going to do an example. So these are our learning objectives for today. But first, a review. Complex power is equal to P plus JQ in rectangular coordinates, and it's equal to the magnitude of the complex power with an angle of theta VI. Now, each one of those terms has a name, has a meaning, it has a specific name, and they are complex power. This is real power or average power. This is reactive power. This is apparent power. And this angle we call power factor angle. Okay. Now, the impedance Z is equal to, in rectangular coordinates, R, which is the real part or the resistive part, plus JX. That's my reactance. In the polar notation, I see that I have a magnitude of that vector impedance with an angle of theta VI. Now notice something about that angle. Theta VI here is the same as theta VI there. This is the same angle, where the definition of theta VI, theta VI is equal to theta V minus theta I. And theta V is the voltage phasor, or voltage phase, and theta I is the current phase in the time domain. Okay. If I were to draw the triangle, the power triangle, in the complex plane, here's the real axis, here's the imaginary axis. Oh, didn't mean to put that in there. And I drew a vector, and I called that vector complex power. That vector has a magnitude, and that magnitude is S with the absolute value symbols, and that's apparent power, and the apparent power units are volt amps. On the x-axis, I have P, or the real axis, I have P, which is real power, and the units are still in watts. The y-axis, or the imaginary axis, is my reactive power, and reactive power is measured in volt amps reactive, or VARs. And that Q is what we're going to talk about today. We don't want that to be too large because it has negative effects on our circuit. So let's drop down here again to our lecture notes and define power factor. Power factor. That it is the portion of apparent power, S, and I like to draw S, my apparent power, as the complex value, the absolute value of the complex power, but it's the same, is actually real power. Okay, whoops. Okay, so my factor, my power factor is equal to the ratio of the real power divided by the apparent power. Another way of looking at it is back to SOHCAHTOA, where the cosine of that angle, theta VI in this case, notice here that it doesn't have it in notes, but that is a theta sub VI, is equal to the adjacent, P, over the hypotenuse, which is apparent power. And that's how I get this equation right here. That's my power factor. And it's a number expressed between 0 and 1. The power factor angle is then given by the angle whose of the ratio, or the inverse cosine of the ratio of power to apparent power. And next slide, next page, we're going to see for pure resistance, inductance, and capacitance, what do those angles look like? All right, so there are three special cases of power factor, so I can get an idea of what we're looking at here in the time domain. So I have in the time domain two sinusoids. One is for voltage and one is for current. Here's the voltage. Whoops, here's the voltage and there's the current. Notice here that theta VI is equal to theta V minus theta I as before. And this is the phase shift of the phase angle of the voltage and current. But notice they're both at 0, so there is no shift. They both start at 0. So 0 minus 0 is 0, so that is my power factor angle. The cosine of my angle 0 is equal to 1. And that's how I get this unity power factor. Notice also that when I have a unity power factor, Q is equal to 0. And power, real power, is equal to the apparent power when my theta is equal to 0. This all occurs when the load is resistive load. Now, going on to the lagging power factor, I see that my voltage and current do have a phase shift between them. And notice here that in this case, my positive half cycle starts first for the voltage right here, and then it's to my current. So if I look at my power factor angle again as theta V minus theta I starts at 0, so this is 0. But theta V is a positive value. If it's positive, then this whole angle, my power factor angle, is going to be greater than 0. When my angle is greater than 0, and I go from the positive real axis in the counterclockwise direction, my Q is also going to be greater than 0. And notice here that P and S are not going to be the same. So in this case, my voltage leads my current in an inductive circuit, an inductive load. So this whole thing is an inductive load. That is for a lagging power factor greater than, power factor angle greater than 0. We also say that's lagging, lag. Okay. The last one shows the current I, starting at 0, is leading the voltage in a capacitive load. So I'm going to call this a capacitive load. And notice here that theta VI is equal to theta V minus theta I. Theta I, again, in this shows that the phase angle is 0. But theta V is going to be negative. It has a negative phase angle. And therefore, my total power factor angle is going to be less than 0. I'm looking over here at the real axis, and a negative angle is going in the clockwise direction from the positive real axis. And therefore, Q is going to be less than 0. Q is less than 0. This is what we call a leading power factor. A leading power factor. Okay, so these are the three types of power triangles that we can see. One with a Q, a reactive power greater than 0, and one less than 0. But why do we even care about power factor? Why is power factor so important? Well, I'm going to do a small exercise to show the difference. I have two loads. Load 1 is shown in this circuit, and load 2 is shown in this circuit. Notice that we're delivering the same amount of real power to both load 1 and load 2. The only difference is that load 1 is a unity power factor, which again means that it's purely resistive, and there it is right here. It's a pure resistor. But load 2 has a power factor of 0.6. That would mean that if it's a positive, which it is, here it's a positive value, this inductor is part of my load. So if I were to find, notice here that in a unity power factor, my apparent power is equal to my real power, and that's 120 kilovolt amps for the apparent power. For the second case, my apparent power in a power factor, in a power triangle, if I were to draw that real quick, notice here that this is P, this is QL, and this is S, equals the square root of the sum of the squares, which is equal to 200 kilovolt amps. Okay. Notice here that my apparent power is greater in part 2 because of my power triangle. Now, if I were to solve the problem, power, apparent power, magnitude, is equal to the magnitude of the voltage times the magnitude of the current. Times the magnitude of the current. And I'm going to use that equation to find my current for load 1 and current for load 2. Now notice the difference. I have 200 amps delivered to load 1, but 333 amps delivered to load 2, and I'm delivering the same amount of power. So what this means is that I need 133 amps more current for the same real power for load 2. So the larger current means larger equipment with wires and transformers and generators, the whole distribution system, which costs more. Also, the larger current also means a larger transmission losses, think I squared R. So in this case, what we want to do is reduce the amount of current delivered to the same load, which we can get by somehow figuring out a way to reduce the reactive power. And there's a clever way of doing that if we simply add the opposite reactive power. In this case, if my load is inductive, I'm going to add a capacitor across in parallel with my load. And that way I'll have a reactive power that's negative, but in magnitude it's the same as the load. And so when I add up all the power, my reactive power cancels to 0. And that's the idea of power factor correction. So let's do a problem. I'm going to follow 4 steps right here to solving a problem like the one shown here to the right. So I'm going to follow these 4 steps, and then I'm going to go back and answer the questions A and B in this problem. Step 1. Step 1 tells me I need to calculate the reactive power, Q, of the load. Now in this case, I want to find QL, right? QL is actually given in the problem. Notice here that QL is 160 kVARs. All right, so I could just state it right here. But instead, I'm going to go ahead and draw the power triangle just so that we can see geometrically how this looks. So this is P is equal to 120 kilowatts. The imaginary part of the reactive power is 160 kVARs. So that's up here. This is QL. PLQL is equal to 160 kVARs. And then if I complete the triangle, the hypotenuse is equal to SL, the apparent power, which is the square root of the sum of the squares of each side. And we've done this in the last problem, 200 kVA. Oh, and by the way, we can find what that angle is. That angle is the inverse tangent of the opposite, or Q, over P, which is 53.13 degrees. If I were to write out what my load, my complex power is to the load, I would say in rectangular coordinates, it's PL plus QL given over here in the triangle, which is equal to the magnitude or the apparent power of that load, 200 kilovolt amps, with an angle of 53.13. Now, I already put that in there, but in general form, remember that that angle is my power factor angle, theta VI. That's the difference between the phase of the voltage and the phase of the current. So that's my general equation for my load. That's step one. Let's do step two. Step two tells me to insert a component in parallel of the load that will cancel out the reactive power. Now notice here that my power, my reactive power is inductive. That's what it tells me in the problem. So if it's inductive, my load, then I'm going to add a load that is opposite of the inductance or capacitance. So I'm going to add to my load a capacitor in parallel with my total load delivered, or my total load. And I'm going to label that with a C, that's my capacitance. So step two, I need to find how much reactance or reactive power I need. So in order for me to cancel completely the reactive power, my result, Q, I'll call that Q sub C for capacitance, reactive power, needs to equal QL, which is equal to 160 kVARs. And now I've solved for problem part two. Step three. Step three tells me I want to calculate the reactance that will give this value of Q. And I'm going to use this equation up here, Q equals V squared over X, for that work. So Q, I want to find the X, but the Q, the problem, Q sub C is equal to the magnitude of the voltage squared divided by XC. Now I know what QC is, and I know what my voltage is, because it gives me in the problem. I'm going to solve for X sub C is equal to the voltage squared divided by QC, which is equal to 600 squared divided by 160 times 10 to the third, which is equal to let me put that over here, which is equal to 2.25 ohms. That's my reactance, X sub C. Now, step four in the problem is then to take that reactance and find the actual value of, in this case, capacitance required to provide that reactance. So X sub C is equal to 1 over omega C, and if I want to find the capacitance, I would say that is equal to 1 over omega X sub C. I know what X sub C is from the previous problem, or from the previous step, and I would need the frequency. Omega is equal to 2 pi f2 complete. It didn't give it in this problem, so we'll call it a day.